Good day, class! Today, I will be discussing Lesson 8.1 entitled Aviation Meteorology Weather's Role in Air Travel. Class, any idea what is aviation meteorology is all about? If none, here it is. Aviation meteorology is the study of weather from the unique perspective of the aviation industry. This information guides the day-to-day operations of pilots, air traffic controllers, airline operators, flight dispatchers, aircraft ground handling agents, and airport operators. Studying of aviation meteorology is rewarding in terms of both saving lives and of reducing injuries, as well as being scientific pursuit in its own right. So class, nakahibaw na jud mo og unsa jud ang aviation meteorology. Okay, let's go back to the history of aviation. Aircraft have been around for a century, but aviation has existed for 2,000 years. Ideas for flying vehicles were being thought of during the Ramayana period. Leonardo da Vinci made over 100 drawings of flight machines. He also invented one of his famous inventions, the ornithopter, which displays his power of observation and imagination, as well as his enthusiasm for the potential flight. Makaingon jud ta class nga grabe jud ka bright og broad ang imagination ni Leonardo da Vinci kay nakahimo man si jag ingani nga butang. Right? Okay, let's proceed. Lighter than air vehicles. At first used hot air but started using hydrogen because it is lighter than air. However, hydrogen is highly explosive and can be triggered by just a spark. On May 6, 1937, Hindenburg, a hydrogen airship exploded and crashed on landing in Lakehurst, New Jersey, United States. Of the 97 persons aboard, 35 were killed. Nowadays, airships use helium, which is an inert gas. The first flight. The Wright brothers, Wilbur and Orville, made the first successful heavier-than aircraft, the Wright Flyer. The first flight was on December 17, 1903. A new era of aviation. With the first flight over, it marked the era of heavier-than-air flight. Modern aviation. When World War II ended, passenger transport became faster and more comfortable. Nagka-high-tech naman ang panahon class, maong nakahimo jud og mga pamaagi ang mga eksperto para mahapsay ang transportasyon og mas komportable ang mga pasahero. Weather information helps to make informed decisions about, first, safety. Avoiding or preparing aircraft for hazardous weather conditions such as turbulence and icing. Second, flight schedules. Adverse weather conditions such as strong winds can cause flight delays or cancellations. Third, flight planning. Wind speed, turbulence, and visibility, among others, can affect flight routes. Fourth, air traffic management. Weather data is used to anticipate and manage congestion, reroute flights, and maintain safe separation between aircraft. Fifth and lastly is airport operations. Weather conditions can impact airport operations, including runway conditions, visibility, and the ability to take off and land safely. Impact of aviation meteorology. Meteorology contributes to aviation safety, efficiency, economy, and environmental protection. Having current weather and aeronautical information in the cockpit helps pilot plan safer and more efficient flight paths, as well as make strategic decisions during flight to avoid potentially hazardous weather.
Good morning, everyone. Today, I'll be going to discuss about the agricultural meteorology, weather and crop productivity. So, this presentation focuses on how weather and climate impact agricultural productivity. It explores meteorological factors affecting crops, challenges faced by farmers, and the tools available to mitigate risk. Agricultural meteorology, the study of those aspects of meteorology that have direct relevance to agriculture. The study of agri-meteorology began as a part of meteorology and agronomy. So, Vasily Dukachev, a Russian scientist, was one of the pioneers in studying soil and its relation to climate. So, in the Philippines, institutions like PAGASA help monitor weather patterns to support farmers. Agricultural meteorology, also known as agrometeorology. So, agricultural meteorology or agrometeorology is essential for farmers in the Philippines where climate conditions vary due to typhoons, monsoons, and dry seasons. Since agriculture is a major part of the Philippine economy, knowing how weather and climate impact crops is crucial for food security and farmers' livelihoods. Agrometeorology is the study of using weather and climate information to improve crop growth and crop yields. So, it focuses on understanding how weather and climate impact crop production, soil health, and overall agricultural productivity. Agricultural meteorology is an interdisciplinary science concerned with discovering, defining, and applying knowledge of the interactions between meteorological and hydrological factors and biological systems to practical use in agriculture. It helps farmers make informed decisions about planting, irrigation, harvesting, and protection against extreme weather events. Agrometeorology helps farmers adapt to weather and climate changes, which is especially important in the Philippines, where typhoons, droughts, and floods frequently occur. Example here is rice farmers in central Luzon rely on rainfall for their crops, but during El Nino, they experience droughts requiring alternative irrigation methods. Farmers use climate data to decide when to plant rice to avoid typhoon season, when to irrigate prevent crop failure, when to harvest before heavy rains cause flooding. Importance of weather in agriculture. So, weather plays a crucial role in agriculture, affecting everything from planting to harvesting. So, farmers need to understand and anticipate weather conditions to maximize crop yields and maximize losses. Let's break down why weather is so important to farming, especially in the Philippines. First, weather determines when and how crops can be grown. So, different crops require specific weather conditions to grow properly. Farmers plan their planting schedules based on seasonal weather patterns. Example in the Philippines, rice farming in central Luzon, farmers plant before their rainy season, June to October, so that crops get enough water. So, mango harvesting and Guimaras. So, farmers pick mangoes during the dry season, so March to May, to avoid excess moisture that can cause fruit rot. Without proper weather conditions, germination, growth, and harvest are affected. Next is forecasting helps farmers prevent losses due to unpredictable weather events. So in the Philippines, typhoons, droughts, and floods can suddenly disrupt agriculture. Farmers rely on weather forecasts to make informed decisions. So example, typhoon warnings from Pagasa help rice farmers harvest early before strong winds and heavy rain destroys crops. Then, drought alerts help farmers in Mindanao decide when to use irrigation instead of relying on rainwater. By following forecasts, farmers can protect their investments and reduce financial losses. Next is favorable conditions results in high yields while extreme conditions leads to crop failure. If weather conditions are stable and ideal, crops grow well, leading to higher yields and better food supply. So, however, extreme weather conditions can damage or destroy crops, leading to food shortage or higher prices. Examples here is Benguet vegetables farms. So consistent cool temperatures allow high quality lettuce and carrots to grow. And in Typhoon Yolanda 2013 destroyed coconut plantations in eastern Visayas, taking years for farmers to recover. This is why climate adaptation strategies such as drought resistant crops, crop rotation, and improved irrigation are crucial. Weather factors affecting crop productivity. Weather directly impacts crop productivity. Different factors like temperature, rainfall, humidity, sunlight, frost, and wind influence how will crops grow and whether they will survive extreme conditions. Let's go through each other factor and how it affects farming, especially in the Philippines. So first, we have temperature. Impact on plant growth stages and yield. So temperature affects seed germination, plant growth, and crop yield. Each group has one optimal temperature range for growth. If it's too hot or too cold, it can slow down growth or cause damage. So examples. Rice and corn need warm temperature. So from 25 to 35 degrees Celsius to grow well, which is why they thrive in Luzon and Mindanao. Lettuce and strawberries grow best in colder temperature like those in Benguet and Bukidnon. High temperatures above 35 degrees Celsius can reduce crop yields, as seen in some drought-affected areas in Mindanao during El Niño. So next is precipitation. Importance of rainfall and effects of drought and excessive rain. Rainfall provides essential water for crops, but too much or too little can be harmful. So drought or lack of rain causes plants to wilt and dry out, reducing yields. So excessive rain leads to flooding, which drowns crops and washes away soil nutrients. And the next is humidity. Humidity affects on disease pressure and transpiration. High humidity increases plant diseases like fungal infections and pests. Low humidity leads to faster water loss, transpiration, drying out crops. Example here is banana plantations in Davao suffer from Panama disease, a fungal infection that spreads in humid conditions. Then, onion farmers in Ilocos experience crop loss when humidity is too high, causing fungal root. Then, next we have sunlight. Role in photosynthesis and growth. Sunlight is essential for photosynthesis, which allows plants to produce food. More sunlight generally leads to better growth, but too much heat can cause stress. So, examples here is the coconut trees in Quezon need a lot of sunlight to produce high quality coconut. Too much shade from other plants can slow the growth of crops like tomatoes and eggplants. Next is frost and hail. So, potential damage to crops. Frost is rare in the Philippines, but in colder areas like Benguet, it can slow plant growth. Hailstorms can damage leaves, fruits, and stems, though they are uncommon in tropical climates. Next is wind. Influence on crops and soil erosion. Strong winds damage plants, break stems, and cause soil erosion. So typhoons and monsoons bring strong winds that uproot trees and destroy rice fields. Impact of weather on crops. First, we have growth stages and weather effects. Germination needs proper moisture and temperature. Drought prevents sprouting, while flooding causes seed rot. Example here is rice. And next, we have vegetative growth. Sunlight and nutrients are essential. Strong winds and heavy rain damage young plants. Example, corn. Flowering. Pollination depends on temperature and humidity. Excessive rain washes away pollen. Fruiting. Heat ripens fruit quickly. Lack of sunlight slows development. Examples, tomatoes. Harvest. Heavy rains can spoil crops. Examples, rice and Nueva Ecija before typhoons. Number two, we have yield and quality. Good weather equals high yield and quality crops. But bad weather equals to low yield, poor quality, and financial loss. Example is too much rain causes mold in onions, drought lower rice production. Number three is extreme weather and damage. Drought. Crops dry out. Example, El Nino 2019 reduced rice and corn harvest. Then floods. Wash away nutrients. Example, Typhoon Ulysses 2020 destroyed rice fields. Frost and storms freeze crops, break trees, and damage plants. Climate change in the agriculture. First, we have effects on crops and productivity. Rising temperatures disrupt planting and harvesting schedules, affecting yields. Soil dries out faster, requiring more irrigation. Some crops may no longer thrive in their usual regions, forcing farmers to adapt. Number two, we have changing weather patterns. More droughts, heat waves, and erratic rainfall make farming unpredictable. Strong storms damage fields and crops. Warmer climates increase pests and plant diseases. Number three, we have adaptation strategies. Developing climate. Resilient crops, efficient water use through irrigation and rainwater storage, adjusting planting schedules and using protective structures like greenhouses. Next, we have meteorological tools for agricultures. So farmers rely on meteorological tools to monitor weather conditions, predict changes, and make informed decisions about their crops. These tools help in reducing risk caused by extreme weather and improving overall agricultural productivity. Weather forecasting and monitoring provides real-time data on temperature, rainfall, wind, and humidity, helping farmers plan planting, irrigation, and harvesting. Agroclimatic data analysis so studies long-term climate patterns to determine the best crops of farming techniques for specific regions. Use of remote sensing and GIS. Satellites and Geographic Information System or GIS help monitor soil moisture, vegetation health, and weather changes, allowing for precision farming. Automated weather stations installed in farms to provide continuous data on local weather conditions, reducing reliance on distant weather reports. Drought and flood early warning systems. It can alert farmers about potential water shortages or excessive rainfall, helping them to take preventive measures. And next, we have climate modeling for agriculture. Uses computer models to predict future climate trends and their impact on farming, allowing long-term planning. Best practices for farmers. We have three key factors. First, crop selection based on climate. Second, water and soil management. Third, protection against weather hazards. First, choosing crops suited to the local climate improves productivity. Example, corn and soybeans needs warm temperatures, while wheat grows in colder areas. Water and soil management. Efficient irrigation methods like drip irrigation conserve water. Organic farming techniques improves soil fertility and moisture retention. And last, protection against weather hazards. Greenhouses and shade nets protect against heat stress. Windbreaks like trees or hedges reduce wind damage. Crop insurance provides financial protection against weather-related losses.
Good day everyone, I am lovely April A. Australias and now we're gonna talk about Lesson 8.3 Disaster Preparedness and Early Warning Systems. Natural disasters driven by meteorological phenomena like cyclones, floods, and droughts pose significant threats to human lives, economies, and ecosystems. The devastating consequences of these events underscore the urgent need for robust and reliable early warning systems or EWS. These systems are not merely about predicting events, they are about empowering communities to prepare, respond, and ultimately build resilience against the impact of natural hazards. Applied meteorology, with its sophisticated tools and techniques, forms the scientific bedrock upon which effective EWEs are built. An effective EWS transcends simple weather forecasting. It's a complex, integrated system encompassing several crucial components: risks knowledge, monitoring and forecasting, communication, and preparedness. First, we have risk knowledge, understanding local hazards and vulnerabilities. This foundational step involves identifying potential hazards specific to our region, analyzing historical data, and assessing vulnerabilities of the population and infrastructure. This requires collaboration between meteorologists, geographers, social scientists, and local communities to understand the unique risk faced. So first, we have satellite meteorology. Geostationary and polar orbiting satellites provide continuous monitoring of atmospheric conditions, including cloud cover, temperature, humidity, and wind patterns. Next to satellite meteorology, we have radar meteorology. Weather radar networks detect precipitation, wind speed, and other crucial parameters at the ground level. Doppler radar meteorology, capable of measuring the velocity of precipitation, is particularly valuable in identifying severe weather phenomena like tornadoes and hailstorms. Lastly, we have data processing and forecasting. The vast amounts of data collected are processed using sophisticated numerical weather prediction or NWP models. These models, based on complex mathematical equations governing atmospheric physics, simulate the evolution of weather systems. So next to monitoring and forecasting, we have communication, disseminating timely warnings to all communities. Effective communication is the most important. Warnings must be disseminated in a timely, accurate, and accessible manner to the target population. This includes utilizing various communication channels such as radio, television, mobile alerts, social media, and community-based networks. The language and format of warnings must be tailored to the specific needs and understanding of the target audience, considering factors like literacy levels and technological access. Then last, we have preparedness, building community response capabilities and resources. EWEs are not merely about delivering warnings, they are about building community resilience. This involves community education, disaster preparedness drills, evacuation plans, and the establishment of effective response mechanisms. Close collaboration between meteorological agencies, emergency management authorities, and local communities is essential for ensuring effective response and mitigation. So what is the role of applied meteorology in EWS? Applied meteorology is fundamental to effective early warning systems. High-resolution satellite imagery provides real-time monitoring of storm development and movement. Numerical weather prediction models generate forecasts by analyzing complex atmospheric data. Radar systems detect ground-level weather phenomena like precipitation and wind. Data assimilation techniques enhance forecast accuracy by integrating diverse data sources. Meteorologists use these tools to provide timely and accurate warnings, empowering communities to prepare for potential disasters. Key components of an effective EWS. Effective early warning systems rely on several key components. A thorough risk assessment, which identifies hazards, vulnerabilities, and potential impacts, forms the foundation. Continuous monitoring and prediction, utilizing technologies like sensors, satellites, and models are essential for detecting and forecasting impending disasters. Warnings must be disseminated and communicated reliably, clearly, and accessibly through multiple channels to reach the target audience. Robust response and preparedness mechanisms, including well-defined plans, community programs, and effective coordination, are crucial for timely and appropriate action. So what are the benefits of an effective EWS? Effective early warning systems significantly reduce the loss of life during disasters. By providing timely alerts, targeted warnings, and clear instructions, EWS enable people to seek safety, reducing the risk of injury or death. This is particularly crucial for vulnerable populations such as the elderly, children, and those with disabilities. With EWS, people have crucial seconds, minutes, or hours to evacuate or take protective measures, minimizing casualties during disasters. In addition to saving lives, EWS also minimize economic damage. By facilitating preparedness, EWS enable authorities to take proactive measures such as sandbagging, evacuating livestock, or securing critical infrastructure. Businesses can also prepare for disruptions, minimizing losses and ensuring continuity of operations. Furthermore, farmers can take protective measures such as harvesting crops early or securing livestock, reducing agricultural losses. By reducing economic damage, EWS help communities recover more quickly from disasters. EWS also play a critical role in enhancing community resilience to climate change and extreme weather events. By raising awareness about potential hazards, EWS encourage communities to take proactive measures to reduce risk. This includes developing emergency plans, stockpiling supplies, and establishing response protocols. Moreover, EWS inform long-term planning and development, helping communities design and build infrastructure that is resilient to disasters. By building resilience, communities can better withstand the impacts of disasters and recover more quickly. Finally, EWS improve disaster response by enabling more effective and efficient deployment of resources and aid. With EWS, emergency responders can prioritize their efforts, focusing on areas of greatest need. Resources such as personnel, equipment, and supplies can be allocated more efficiently, and a coordinated response can be facilitated among emergency responders, government agencies, and other stakeholders. This reduces confusion and duplication of effort, ensuring that aid reaches those who need it most. Now let's move on to the types of natural hazards and its corresponding EWS. First, we have earthquakes. Earthquakes are a significant threat to communities worldwide, and earthquake early warning systems, or EEWS, like Shake Alert, play a crucial role in mitigating their impact. These systems detect the initial less damaging P wave that precedes the more destructive S wave, providing a vital window of time for people to seek safety. By quickly estimating the earthquake's location, magnitude, and expected shaking, EEWS can alert authorities and the public, enabling them to take necessary precautions before the S wave arrives. Next, we have floods. Floods are another type of natural hazards that can have devastating consequences. Flood warning systems help mitigate this risk by using automated sensors in rivers and reservoirs to collect and transmit data. This data is then used to generate forecasts, which are then disseminated to authorities and communities, enabling them to take necessary precautions. In addition to these technology-based systems, community-based initiatives such as those in the Hindu-Kush-Himalayan region focus on specific flood risk like glacial meltwater lake outburst. These community-based systems rely on local knowledge and observations to provide early warnings. Next to flood, we have tsunamis. Tsunamis are rare but potentially catastrophic events that require rapid detection and response. Tsunami warning systems, or TWS, utilize a combination of seismic stations, seafloor pressure sensors, and tide gauges to detect and confirm tsunamis. By processing data from these sources, TWS can provide accurate forecasts, enabling authorities to evacuate coastal areas and take other necessary precautions. The use of advanced technologies such as deep ocean assessment and reporting of tsunamis, or DART buoys, has significantly improved the accuracy and speed of tsunami warnings. Then lastly, we have cyclones. Cyclones, also known as hurricanes or typhoons, are powerful storm systems that can bring catastrophic winds and rainfall. Cyclone detection relies heavily on scatterometers, satellite sensors that measure surface wind speed and direction using microwaves. This data is crucial for forecasting cyclone intensity and track, enabling authorities to issue timely warnings and evacuate vulnerable populations. By combining data from scatterometers with other sources, such as radar and weather stations, forecasters can provide accurate and reliable warnings, helping to mitigate the impact of these devastating storms. So in conclusion, effective EWS are a collaborative endeavor requiring the expertise of meteorologists, other scientists, emergency managers, and local communities. By leveraging advancement in technology and strengthening collaborations, we can build more resilient communities and minimize the devastating impacts of natural disasters. The continued development and refinement of AWS, with applied meteorology at its core, are critical investments in the safety and well-being of populations worldwide.